Okay, this is Professor George Adams again with a demonstration to show you on impact. Now here we have a basketball and a tennis ball. Now, from what you know about the coefficient of restitution and impacts, you know that if you had a perfectly elastic collision, for example, with this basketball on the ground, if I dropped it from a height of 4 feet, it would rebound to a height of 4 feet. Now in reality, of course, that doesn't happen because some energy is dissipated during the impact. And the ratio of the separation velocity, that is the relative velocity between the basketball and the ground immediately after impact, to the approach velocity, that is the closing velocity immediately before impact, that ratio is called the coefficient of restitution. And for a perfectly elastic collision, that coefficient of restitution would be equal to 1, in which case the process would be completely reversible. You drop the ball from a height of 4 feet, it would rebound to 4 feet. In reality, of course, some energy is lost. And the same thing, of course, would be true for the tennis ball. Drop it from a height of 4 feet. If it were perfectly elastic, it would rebound to a height of 4 feet. Now what I'm going to do is a little bit different. I'm going to hold these two together, the tennis ball on top of the basketball, drop them, and we'll see what happens. You might think that again you would get a height of rebound which is less than the height at which you dropped them from, but let's see. Okay, well, I'm not sure how well that was captured, but as you can see, the tennis ball went flying off, whereas the basketball seemed to rebound just as it otherwise would. And that phenomena is a little bit difficult to explain, but I'm going to give it a try. Okay, so there are actually two impacts involved. In the first impact, the basketball hits the ground and rebounds. Now, if we, for simplicity, assumed everything was perfectly elastic, then the rebound velocity of the basketball from the ground would be equal to, let's call it V0, upward, which would be equal to the downward velocity with which it hit the ground. Just slightly after that, though, the tennis ball is coming down with that same velocity V0, and the basketball is going up with a velocity V0. Now, if you do that impact, if you analyze that impact elastically, because the mass of the basketball is much greater than the mass of the tennis ball, you would expect then that the relative velocity after the impact is the same as the relative velocity before the impact. Now let's think about that. The relative velocity before the impact is 2v0, right? Because the basketball is moving up at v0, the tennis ball down at v0. So the separation velocity, the relative separation velocity, should be 2v0. Not v0, but 2v0. Furthermore, the basketball, since it has a much greater mass than a tennis ball, is not much affected by that second impact. So that the relative velocity of the tennis ball with respect to the basketball being 2v0 gives you an absolute upward velocity equal to 3v0. Now, of course, that assumes two things. It assumes perfectly elastic collisions, and it also assumes the mass of the tennis ball is much less than the mass of the basketball.